Hello and welcome to follow my video course Introduction to Flow Mechanics. My name is Matti Ylitalo and I'm your teacher during this course. Today our focus will be on radiation heat transfer. Radiation heat transfer is very important when we have hot bodies, but it can be also very important in case when we have moderate temperatures, but our conduction heat transfer and convection heat transfer are small, then the effect of radiation can be very important. The basic of the radiation heat transfer is the so-called Blackbody radiation. It's saying that every single body which temperature is above the absolute zero is radiating to environment. This radiation is proportional to the fourth power of the temperature of the body. And for real bodies we use so-called emissivity factor. So real bodies are not emitting so much. This black body is some kind of ideal body. And for real bodies, these emissivity values are typically 0.4, 0.8. But there are some materials which has very high emission value. For example, this charcoal powder has emissivity 0.96. It's almost black. Everybody is emitting radiation to environment based on its temperature, but everybody has another feature also. They are absorbing heat or radiation from environment. This absorption is proportional to the fourth power of environment. The environment can be here the gas phase around the body, or it can be another body also. When we are calculating heat fluxes, we typically assume that emission coefficient and absorption coefficient are equal. This is the so-called gray surface approximation. We can write for heat fluxes a function, and here we have now this emissivity coefficient, surface area, so-called Stefan Boltzmann coefficient, but we need to know the temperature of our body and the temperature of environment. Be careful here, this is not the temperature difference, but we need to know both temperatures. In this picture we have one possibility to describe what happens to radiation. Part of the radiation is absorbed, part is reflected, and the rest is transmitted. For black bodies, this transmitted and reflected part is zero, and all is absorbed. For real bodies we have very large range of absorption coefficient. It can be very low, as for polished copper for example, it is as low as 0.03. But for typical materials this absorption coefficient is around 0.4, 0.8. And typically in industrial application we have some deposition layer on the surface, and for that kind of dirty surfaces the absorption coefficient is typically in range 0.8, 0.9. but in some cases it can be even 0.4. To fresh up our mind, I added a picture showing the wavelength spectra of radiation. On the other end is a very short radiation wavelengths for gamma rays, X-rays. Then we have our visible wavelengths, which is a narrow part in that wavelength spectra. And then we have infrared, and on the other end of this line we have very, very long wavelengths. It's good to remember also the Wien's law. Wien's law is telling to us that when the temperature of the body is increasing, the intensity maximum is going towards shorter wavelengths. For example, our Sun has surface temperature around 5800 degree Kelvins, and from this figure we can see that it has the maximum at around 500 nanometers. To calculate the heat transfer by radiation, we need to know the so-called view factor. This view factor tells how well a body can see another body. And view factor from surface 1 to 2 can be defined as a fraction of area A2, which area A1 can see. For these view factors we have the so-called reciprocity rule, which is saying that the surface area A1 times the view factor from this A1 to surface A2 is the same as the surface area A2 times the view factor from this surface 2 to 1. There are some special cases in which the surface can see itself. If we have a plane surface that will never see itself. The same is true also for convex surfaces. But if we have concave surface, that can see itself. Let's take a simple example of these view factors. We have here a hemisphere, and we want to calculate how well the hemisphere surface will see itself. In this case we have the surface 2, which is a plane surface, and it will never see itself, so we can set f2 to 2 is 0, then f2 to 1 must be 1. So the surface number 2 is seeing only surface number 1. But how well surface number 1 is seeing itself? We know that the sum of the view factors is always 1. And we have this reciprocal rule. Now we can calculate the surface areas. We know that for this plane surface we have surface area which is proportional to the radius of this circle, and we can also calculate the surface area of this hemispherical area. And we will see that the surface area of this hemispherical area is 2 times the surface area of this flat bottom area. and from this reciprocal rule we will get that F1 to 2 is proportional to surface areas times this view factor 2 to 1. We now have F1 to 2, and we already calculated that A1 is 2 times A2. We can use this in our equation 1, and we already know that F2 to 1 is 1, so we will get that F1 to 2 is 0.5, and because the sum of the view factors must be 1, we will get that F1 to 1 must be 0.5. To get the view factors we can use tables, or we can search view factors from publications in net. Here is a link to a very good example that the publication is giving view factors for different geometries. For example, for this kind of concentric coaxial cylinders, and for parallel rectangular plates. It's of course possible to start a discussion with AI tools. Nowadays they are very good tools to get help in this kind of a situation. Here is one example. I calculated the heat flux between parallel plates. The plate 1 was 1 times 1 meter and plate 2 was 2 times 5 meter, and the distance between plates was 2 meters, and the plate temperature was varying from 100 to 800 degrees C. I sent a request to ChatGPT to develop a Python code to calculate this, and with that Python code I calculated the heat flux as a function of plate 1 temperature. Here we can see the result. Okay, thank you. That was all today, and see you again. Bye bye.